do that. Yeah, just let me know when I should begin, and I'll just ramble on.
You can start.
All right. Hello, folks. Welcome. My subject matter is optimization-based control, and I will give you an introductory lecture on this particular subject. I thank the organizers for the opportunity they have offered me to give this particular lecture. Many thanks. And I think Abhijit asked me to say something, to speak about something at the intersection of optimization and control. And hence, therefore, I have chosen optimization-based control, which is a reasonable synthetic amalgamation of both. All right, so let me go forward. The way that this will go is I have some slides, and I will be writing on the side and on the slides themselves as I go along. And if you have any question, please just ask. Okay. Okay, so here is the contents list. I'm going to go through a general introduction, make some general observations after that, and I will talk about linear models and nonlinear models separately, and then talk a little bit about regulation properties, regulatory properties, and tracking properties maybe, and some robustness aspects of this particular mechanism, and then finally conclude with some references. Okay, so here is the introduction. I will begin with the usual architecture of control. What does it have? It usually proceeds as follows. The design is offline, okay? And maybe this is a good opportunity to take one step back and maybe draw a block diagram here. Block diagram here is this particular dynamical system, and we would like to actually control this particular system with a block, which we usually label as K. And there is this particular output, Y. This output is usually fed into this particular block, which is usually known as the controller. This controller sends out a regulatory signal in order to control this particular system. And there is an input signal here, okay? Now that's the usual block diagram of control systems, which you will find all over the place. Now, what do I mean by this design is offline? What is offline about this? Well, this particular block K that I have here and that I will highlight in yellow right now, this particular block is actually designed offline, okay? And the online implementation is usually very easy, very simple. It most of the time consists of linear gains, okay, and evaluation of certain maps, etc. So this particular block is simple in general, as simple as possible. And it makes sense to make it simple because if it is very complicated, it is very complex, then the online operation may be just because this needs to be computed very fast. This particular signal, this if you allow me, I will write this as U and this as R. R is the reference input and U is the action which this block sends into the actuator. Yeah. So this the online implementation is most of the times easy, simple. If this particular object, object here is linear, then it makes sense to keep this block K also linear, and it just means that it just introduces a linear gain into the system. That's all. Now, there's a downside of this particular approach, and the downside is that certain restrictions on the on the space variables and the action variables are not very easy to incorporate at the design phase. Okay. Now, this is very well known, and that's the classical mechanism of going about things. And when I say classical, I don't mean frequency domain approach. It is just simply classical by it's labeled as classical for historical reasons. That's all. Hmm. Now, there's a point of departure is observed when optimization enters into the fray. Things become optimization based. So where is optimization? I'm going to mumble about this throughout the next maybe 80 minutes or so. So at this moment right now, I'm going to give you a very brief outline. This optimization based module replaces this particular K. Okay, and the design is offline, but you will see that there is a huge difference. Okay, this particular K is replaced by a non-trivially complicated module called optimization-based module. Optimization-based module. Okay, this I have to mention simple in classical approaches. And because these classical approaches cannot handle certain restrictions on the space variables and the action variables very smoothly, very nicely, the need was felt to augment this particular block with something else, to supplement and augment as needed with something else. And engineers came up with this particular object called this optimization-based module. All right. Now, one of the key features of this optimization-based module is that the computation of the actuator inputs are actually online. They are done online. And naturally, these things require greater computational apparatus. On the plus side, and this is really the key, various kinds of restrictions on the space variables and the action variables are integrated at the design phase itself. So if you ask that this output Y must respect certain boundaries, and these boundaries could be due to anything, let's say for safety reasons, a robotic arm should not move at extremely high speeds, then that is a restriction on the space variables of this underlying system, isn't it? So these kinds of restrictions are easily integrated at the design phase, okay, in this particular module, which is optimization based. Okay, so that's a very broad introduction. Let me move on to an example. And this example, I believe most of us will be happy with, or at least you can identify yourselves with. So driving a car. Imagine that you are driving a car. What do you do? You can ask me, am I driving on Indian roads or am I driving on the roads in the West? Because there are dramatic changes according to the geographical location. Let's say that you're driving on an Indian road. So there are certain operational demands, operational requirements from the driver. First of all, speed limits need to be respected. As much as I would like to say that, yeah, in India, there is no need for doing that, that's not true at all. Okay, so we do indeed need to respect speed limits, number one. And number two, in the interest of not causing hassles for everybody else, it also makes sense to just go with the flow. Just follow the ambient speed of the traffic around you. One has to maintain some kind of a separation between vehicles, especially in front of you, which is this. Whoops, which is this. It would also make sense to adhere to your own lane, which means this. And then finally, we should not really hit other vehicles or the side of the road, or let's say there's a bull on the road, which is just sitting there for no reason whatsoever. We should not hit hit him either. So what exactly is going on in our brains as we drive? Bear with me. I will try to sketch this for you. Uh, Please try to see whether you agree. Let's say that the road is given like this. Okay, there is a gentle curve ahead. That's the boundary of the road, and let's say that this is the center line. Is my screen visible to one and all? I hope it is. Is it okay?
Yes, it is to me.
Okay. So let's say that there is a car here. All right. So this particular car, and of course there's significant traffic, let's say here and maybe some places ahead. What does the driver do? Let's say that this is a left side drive, so this car is trying to move towards the right. What does the driver do? The driver looks ahead a little distance, maybe the vehicle in front, maybe even a little bit beyond the vehicle in front, maybe a few vehicles in front, and also the oncoming traffic in a certain way. Maybe this much of region is really within their vision. The driver plans the next few actions. Okay, and by next few actions I mean actions which he or she is about to go forward with for the next few seconds, maybe moments, seconds, milliseconds, depends upon the ambient speed. Next few moments. Now once this particular plan has formed in their mind, they will execute it. Okay, and as they go forward executing this particular, they will revisit their plan because the module has probably changed. This scene ahead has probably changed once they reach that particular location. Okay, and that, and then maybe that becomes the new look ahead region. Okay, now look ahead region is both in terms of space as well as uh, time. Okay, because maybe the driver, when the driver was here, they had planned a little bit short, short horizon ahead because there's a gentle bend. Okay, bend really coming up, and simply because they can't really look beyond this particular bend, there is no question of really planning for what's beyond the bend. Okay, now when the driver goes forward a little bit, the horizon may will definitely change, and a new plan will be necessary. Is this reasonable enough? I'm trying to say that as we drive on the road, each one of us is trying to plan just a little bit ahead, okay, and simply execute the planned actions just a little bit for just a few moments. Observe what has really come up in front of us, okay, and then make a fresh plan, then execute it again iteratively. I think you will agree with me that this is a reasonable course of action, and that is what we implicitly do. And by we, I mean our brains have really become trained to do this implicitly. Okay. And during our actions, while we are driving on the road, while we act, we are actually trying to save ourselves from the side of the road, from really veering out of our lanes, okay, respecting the speed limits, going with the flow, and of course trying not to hit um, other objects on the road. That's how we usually plan ahead. Now this is exactly the nature of things that is done in optimization based control. Exactly this. Let's see. Here are the features. Look ahead a little and then plan. Execute the appropriate actions, rectify, replan, and iterate this process. I think there's a question. Yes, please go ahead. I could not hear you. Is there a question?
I think there was some noise in the background.
I see. Okay. All right. All right, so let me revisit this particular slide. Okay, the operational demands on the car were of course given, and these are very rational demands. The way that we drive is naturally of this particular form, as I've elaborated in these three bullets here. We look ahead just a little bit, not very much. Let's say that you want to reach uh, how should I put this? If you want to reach your airport, nearest airport, now obviously when you're on the road, you don't see the airport unless you're living really too close to it. Then what do? You are not able to see the airport in one shot. However, you have a general sense of which way you need to go. So that general global sense is already inside your head. And then the local actions will have to be done. You have to go through the traffic, through the road, yeah, and you have to arrive at the nearest airport. That's the job. How do you do that? You look ahead a little bit and then plan, execute appropriate actions, rectify, replan, and then iteratively go forward with this nice little scheme. Okay. What sort of plan? I said plan. What sort of plan? We are lazy people. Every human being is lazy, naturally. And there is no second thought about it. Everybody is lazy. Also, everybody wants to save money. Almost everybody wants to save money. So minimizing fuel, energy, minimizing exhaustion, yes, these are naturally parts of the plan. Also part of the plan would be to remain within the boundaries, which are of course given in the operational demands. So remaining within the boundaries of operation. I'm not going to drive a car at breakneck speeds through literally dense traffic. Surely not. That would be madness. Yeah. And of course, I'm not going to plow through the traffic for obvious reasons. I actually respect everybody around me, naturally. So this is the kind of a plan that would make sense. And what is done in optimization-based methods is exactly this. Exactly this. Let's try to get into this, jump into this. Here's the cartoon diagram, and I will draw this particular cartoon online. Let's say that we have the time axis here, and I will draw this maybe at three different places. Here's the time 0, 0, 0, 0. At time 0, the plan is to look ahead for this distance. Let's say a horizon of length n. Okay, this is the planning horizon. Do we execute all of the actions which we are actually planning during the horizon? Most of the times, no, because the field of view is actually constantly changing, and there is a natural way to adapt in our brains, adapt and then look ahead, maybe for so long, but then we don't act all the way. We act only a little distance, maybe here, and then replan for the same length, which is the length remaining constant, roughly speaking. This is roughly speaking what we do, but there are variations. You can ask me, why is this n the same length as that particular n? Well, this is a simplification. but there is no a priori reason to actually use the same horizon all the time. Horizon of what? Horizon of plan. So and then in fact me uh, let me introduce this particular word, horizon. This is the planning horizon. This is the planning horizon. N. Okay, and this is the we act during this particular time. Okay, okay, plan again from here to there, and then act again from here to there. This is action, and then again move, slide the window. Okay, slide the window again, n long, and then act during uh, this particular initial phase, and then move forward, replan, etc. Yeah. Now that is what we usually do while driving a car. Optimization-based methods is some kind of an abstraction of this mechanism, which I will introduce next. Okay, is there any question so far? Right. I should mention that I should mention here, maybe I should write down even before this production. Okay. Huh. Optimization-based control. This is also, AKA, also known as model predictive control. Model predictive control, receding horizon control. Variants of this are also called rolling horizon control, etc. Yeah, also known as this is the most popular abbreviation, MPC. This is called RHC, receding horizon control, or rolling horizon control. Various different ways of saying the same thing. I should mention that the concept of receding horizon control originated in the operations research community, I think in the 1950s. And then in our community, it did not become very well known. It did not gather traction because of the absence of computational algorithms in order to really compute and plan and then act very fast. So it actually took literally years, decades, and now most industries are espousing this particular method in favor of the classical methods of PID control and other stuff, and for quite clear reasons, which I will enunciate later. Okay, so here is it's of course. Now we should jump into some symbols and a little bit of, let's say, mathematics. Well, this is not mathematics, this is just symbols. So let's go into a few symbolic representations. System model. This is the system, or this is the dynamical system. Okay, this is the dynamical system. The block that I had written first, that's the system, where here are the action variables u. Okay, the this object is completely described by a vector of states, which we are going to write as xk at time k, xk. Now, in the diagram before, I had drawn some kind of an outward arrow and then labeled a y here. Y is usually the outputs. Here, for the sake of simplicity, I will simply put y is equal to x. Okay, so the idea is that I'm observing all of x. Okay, and it is not a restriction. One can do much more refined things, but that's not the subject of this talk. So system model is going to be given by this iteration. Xk plus 1 is equal to f of xk and uk. Now, xk, as I was mentioning here, xk is the vector of states. This usually takes values in some Rn. uk is the vector of control actions. This takes values in, let's say, Rm. So what is f? F is a mapping. F is the underlying system. Rn is a mapping from Rn Cartesian Rm into Rn. Okay, and this is the system. The mathematical representation of the system, also sometimes known as model of the system. Please recall I'm sorry, I think I should make this at time k. Yeah. States in Rn at time k, add time k, at time k, k, etc. Now, for simplicity, here we will look at f, or the model, being time invariant. If this particular model is time varying, then f should also become a mapping of another argument which keeps track of the instance. We are not going to get into that complication here. For operational reasons, as I was mentioning in the driving example, there are certain restrictions on the action variables and the space variables. This is, I'm going to say that x is the space variable for obvious reasons, because Rn is the space of all possible states, state space. Okay. So certain restrictions on the space variable and the action variables are always enforced. Always. Notice that in the example of driving a car, the road was given in front of you, and that naturally enforces some kind of a restriction on where you can go on the space variable. Literally, the space variable, the space available to the car. Not only the road, there is also a lane which one is supposed to respect, which means that this particular natural restriction is more how should I say, rigid now. Yeah. Action variables are also restricted. Action variables are restricted because a car is an inertial object. If you want some sort of a blistering acceleration immediately, that's not going to happen. It is definitely not going to happen. Also, brakes are important. Brakes should be good, but the brakes cannot be extraordinarily good, and they should not be really extraordinarily good. Otherwise, you would hurt yourself. Yeah. So there are, of course, restrictions on the space variables and the action variables. Of course, there are restrictions on the speed of the car, which is one more example of space restrictions. Okay. So the idea, what is the idea? The overarching idea that I was mumbling about in the previous slide was to minimize a certain objective function. Okay, we want to drive, and let's minimize a certain objective. That objective could be minimizing fuel, minimizing, let's say, energy expenditure, minimizing money, minimizing our own exhaustion, etc., while satisfying certain restrictions on the space variables and restrictions on the action variables. Yeah. Notice that I have labeled here sum from 0 through infinity. Okay, plus infinity sum. Okay, cost function. This is a cost function. I should change the color, and I should label the C as a cost function, cost, or an objective function. Okay, infinite horizon cost. I'm trying to minimize this. It's a very nice idea. Unfortunately, it's a dead end. Okay, and let's move to the next slide. Okay, the next slide is in the next page here. All right. In general, and that's what I would like to emphasize here, in general, this problem is impossible to solve. What is the problem? The problem was, recall, minimize the summation of cost per stage functions, xk and uk. Okay, subject to, let's say x at time k belongs to some set x, and u at time k belongs to some admissible action set u. This problem now is impossible to solve. Why is it impossible? What is the minimization over? Well, the minimization over is actually over the set of actions uk, k0 through infinity. The set of actions spread across all time. Yeah, this is of course literally, okay, it really cannot be solved. Why? Because there are infinitely many variables. This is a no-go. No way. No way can this be solved. Yeah. So this is the, it would be nice to be able to solve this. That would be an ideal situation. Unfortunately, this is impossible. So we have to settle for something that is less than ideal. Such is the way of the world. That's nothing new. And what is the way forward? The way forward is, well, one of the ways forward is to settle for suboptimality. Okay, what are the things that we like? What are the ideas, the overarching ideas that we like? We like the idea of constraints. These are extremely important in practice. Whosoever has driven a car on the road knows that, okay, there are natural restrictions on several things which the driver must face and must respect. There is no way otherwise. None. Yeah. So all of these constraints must be seamlessly sort of integrated into any framework that we wish to adopt. So of great importance, one of the chief ideas is to incorporate these seamlessly as one can. Suboptimality. Okay, optimality and suboptimality. There's this particular huge debate about whether things should be optimal or one can settle for suboptimality. Okay, what good is an optimal solution if we can't solve it? If we can't arrive at it? Well, here is an ideal case. This is an ideal situation which literally cannot be computed. That doesn't mean that we will not try to attempt to solve this particular problem. It is an important problem. It is an important objective in engineering. So let's try to solve it. It'll be nice to keep these two. Let's settle for suboptimality, meaning let's modify this particular optimization problem, the objective, to suit our resources. That's what we will do in optimization-based methods. Truncate the infinite horizon to a manageable one. So the horizon was all time. Okay, it was over all time. What was it? It was some, if you recall, the cost function was x of k and u of k. Okay, and the sum was over all time. And naturally, this was not solvable. So let's go with some suboptimal solution. We will truncate this infinite horizon to a manageable one. What now? Impossible to solve. That's impossible to solve. Truncate the infinite horizon to a manageable one. What kind? Let's see. Why not do the following? Okay, k equal to 0 through n, x of k and u of k. Okay, and then try to minimize and also really mimic the actions of our driver on the road. We keep shifting the horizon, rolling the horizon. Okay, not shrinking the horizon, shifting the horizon, recede the horizon over. So plan for this length of a horizon and keep shifting the horizon. Am I making sense? So that's what we will do. And here at once, immediately, we have a lot of trade-offs and a vast lot of engineering hacks. Lot of engineering hacks. This how should I say, regime, this method is full of engineering hacks, and for good reason. Okay, let's go forward and have a look at what kind of hacks, etc. So lots of trade-offs and engineering hacks. We would like to keep a firm grip on the restrictions. Okay, suppose that in the space variables, let's say that xk was required to lie in some set, let's say uppercase X, and let's say that that particular set was this. Okay, now please notice, and I have just drawn this in R on the plane R2. Okay, and that's the shaded part in yellow. You should see this at once that this is a non-convex set. Non-convex things are not easy to handle. So sometimes, and it makes sense for 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 let's say ease of of our hardware to do some kind of an inner approximation of this particular set, which are of this kind. Okay. So xk belongs to this particular x. If I replace that particular requirement by xk must belong to this brown shaded region, then of course this particular objective, which I had before, is going to be restricted. But the representation of that yellow set, which is non-convex, is much harder than this particular intersection of these hyperplanes, which is much simpler because I have to keep track of certain offsets and certain slopes. That's all. Yeah. So sometimes, if it makes sense to do certain inner approximations as needed, if needed. Okay. And then, well, there's this particular object notion of the horizon. What was the horizon? That was the planning horizon. Okay, how does it affect us at all? Well, if that particular horizon was arbitrarily big, then we obviously could not at all compute. If this particular horizon is large, then there are a large number of these action variables which we have to choose from, meaning the the space of optimization variables increases. Okay, and it it should be a very natural observation now that instead of doing that, it makes sense to have a reasonably short computation, short horizon in order to minimize the effort needed to arrive at solutions. So this n, that's the horizon. Horizon should be short enough. And how short? Well, there are trade-offs. As I was mentioning here, trade-offs. If you keep the horizon to be too short, then there are issues of jittery behavior. Okay, because the look ahead is very short and therefore myopic. So the planning is very jittery. Okay, in broad strokes. And in fact, there are good reasons for it, which I will not be able to get into in course of this particular talk, and etc. So I have really kept these three dots to mention that there are many trade-offs, many uh, and of course hacks. Okay, hacks, heuristics, all kinds of things. Now, it may appear to a mathematician that these hacks and heuristics are not good ideas. Well, maybe mathematically not, but then for practicing engineers, maybe they are relevant. So it is not a very good thing to say that, okay, blanket, no heuristics. If there are heuristics, our efforts should be to quantify them and to make them rigorous. Yeah. All right. Okay, so let me move to the next part, which is linear models. Linear model. Is there any question so far before I launch into linear models? Because we will have a lot to do here. Any question?
So there is one question in the chat box.
Please. Okay, then let me read it out in the chat. Okay.
Can you
Pure pursuit control as an optimal controller, as it also deals with look ahead distance. Yeah, can you tell pure pursuit control as an optimal controller? Pure pursuit control, you have to educate me about this particular subject, because I have heard about these kinds of games, but not this phrase that you have written here. If in fact the game is the one that you are trying to refer to, yes, a game is naturally regarded as an optimal control. In fact, more than that, it is a game. So there's a min-max problem, which is being solved here. Sure. Yes. And the min-max problem is not very far away from what we are doing. I will be able to remark on it very soon. Yeah. Does that answer your question?
Mr. Shiva Palani Rajan, you can unmute yourself and discuss. I mean, we encourage that.
Yeah, please.
Okay. So he says, okay, sir.
All right. Okay. Anything else? Any other question? All right. Before I think it makes sense to go back here and harp on certain things that I may have glossed over. Let me see. General observations. Okay, let's go back to the introduction, the last slide of the introduction here. Uh, The blue highlighted object is the recursion or the iteration which actually describes the underlying process that is being acted upon. It is being acted upon because if you let it free, meaning UK is a sequence of zero controls, zero actions, then things will not be very pleasant. Okay, so that's why you are trying to introduce action variable to UK. All right. And this is a model. This model could be linear, could be nonlinear, could be anything. It will depend upon what you are trying to act on, what object. Yeah. We have these restrictions on xk and uk on the space variables and the action variables, and that's the green highlight now. Finally, there's this particular cost function, which I will highlight in light red right now. Okay. Now, this particular cost function also is just written in an abstract way right now. It's your call. It's the designer's call. It's the engineer's call. What kind of an objective makes sense in your problem is for you to decide. Okay. I'm going to speak a little bit about certain linear models where this f here, this f object here is going to be linear, and this c here is going to be, let's say, quadratic. Why quadratic? Because it's the simplest possible setting. The method is not restricted, and I repeat, this is not restricted to linear quadratic problems. Okay, please do not be under this particular impression, and it will be a completely false impression that this method is restricted only to linear models and, let's say, C being quadratic. Absolutely not. Absolutely not. Not only that, here so far in my lecture, so far I have only kept purely deterministic models without any noise and uncertainty and all that stuff. It is very easy to introduce uncertainty right here. Okay, and maybe as I go through the linear part, I will try to do that. Let's get into the linear models because I think I need to rush a little bit. Okay, this is the framework. On your screen is the usual framework of linear model. So linear model that's the linear model. In the green highlight, in the light red highlight, I had kept the cost function. So here it is, the cost function and certain constraints. And the constraints last time were in green. So that's the uh, that's the link between these objects. Okay. Uh, so linear model, yes, it's a linear system, linear invariant system. So A and B are not changing with respect to K, and the cost functions are quadratic. What kind of quadratic? What is Q and what is R? Let's see. Here we go. Right, that's the cost function. This is the equation. That's the this iteration. And this is the set of restrictions on the action variables and the space variables. Okay. Now I've said here linear slash ellipsoidal constraints. Linear slash ellipsoidal constraints would be how these sets uk and xk would be actually described. If xk is an ellipsoid, what is an ellipsoid? Okay, let's say that x is given by, let's say, x1, x2 in R2, such that x1 squared plus x2 squared is bounded, or let's say 3x1 squared plus, okay, 2x2 squared is bounded above by, let's say, 4. And that's an ellipsoid. Okay, that's an ellipsoidal region in R2. Yeah, and of course, 0 is right at the center. It's how it'll look. And linear constraints would look something like intersections of certain half spaces, which means that that's the kind of set that we are looking at. That's our X. Not the shaded part, but the unshaded part. Okay. You might ask me, are these all the relevant ones? Of course not. Of course not. But then these are the most frequently used, and these are the most frequently used because these are the most natural ones in realistic operational models. Okay. So, and of course, these will be accompanied by certain assumptions. The assumptions are here. Q. What is this particular Q? Q is a matrix. It is a non-negative symmetric. This is positive semi-definite matrix. This R is a matrix, is also a matrix. It is symmetric, and this is positive definite. And certain other restrictions on this particular pair AC, etc., etc. These are all usual stuff. I'm not going to go really over them here. I'll try to explain what the basic idea is. And of course, X and U, these are the restrictions on the space variables and the action variables. These are most of the times, well, for most of the times they will be actually convex. All right, so linear models. Okay, now what? We have written down this particular problem. We would like to translate this particular problem into something that an optimization solver can solve. Is this problem in that form? The answer is, well, maybe, but it needs to be massaged a little bit. So what kind of object are we looking at? This is an optimal control problem. We want to translate this particular problem into a quadratic program. Okay, why? And it's a Q or a QP. Okay, this is a quadratic program. This is an optimization problem. So control problem changed into an equivalent optimization problem. Hence the word optimization based. Okay, how do we go about doing this? This is very easy. So let's see, what is x0? X0 is of course given to us. That's that initial, let's say, boundary condition. This is given to us. What is x1? X1 is equal to a times x0, of course, plus b times u of 0. The zeroth action, or the very first action, is going to influence x1, of course. What next? There is x2. X2 is equal to a times x1 plus b times u at 1. The first action, or u at 1, is going to naturally influence x2. Sure. So by using this particular model, linear model, I can iteratively write down what is x0, what is x1, what is x2, etc., etc. Yeah, all very, very natural and very easy. At the end of the day, what do we get? This is xk transpose q xk plus uk transpose r u of k, and there's a sum. Okay, sum k equal to 0 through maybe n. Fantastic. Do you see that this is equal to, just in one shot, this is going to be x at 1, x at 1, x at 0, x at 1, x at 2, all the way through x at, I don't know, n. Yeah, transpose. Then there's a huge matrix of, let's say, q, 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 etc., all the way through q, or everywhere else zeros. And there's x at 0, x at 1, all the way through x at n. Okay, that's that sum, plus there's a u0, all the u at, oops, u at 1, all the way through u at n minus 1. Oh, okay, n, all right. And there's an r, etc., the block diagonal matrices. Okay, and there's a transpose here, and there's a u0, u1, u at n minus 1. Okay, do you see that this particular sum is exactly equal to that? I think this should be fairly straightforward. Yeah, because this matrix is block diagonal. This matrix is also block diagonal. These are gigantic matrices. I understand, but that's okay. That's all right. Well, I have not eliminated x0, x1 all the way through. Let's do that now. So there is x at time k. This is equal to a to the power k times x0 plus, I want you to observe this very carefully. This is a to the power k minus 1b, a to the power k minus 2b. These are block matrices, of course, and then there's b of u0, u1, all the way through u at k minus 1. Would you agree? Yeah, okay. Please remember that this is un. Yeah, so that's this. Xk is given in terms, is now affine in terms of the initial condition x0, and there's this matrix, okay? There's this reclined matrix which multiplies this particular tall vector of u0 all the way through u at k minus 1. Okay, so what is this vector now? That vector is naturally, okay, do I have space here? Yes, of course I have space here. So this is x at 0, x at 1, all the way through x at n. This is going to be equal to identity times x0. This is a times x0, sorry, all the way through a to the n. Yeah, plus a gigantic matrix of what? U at 0, U at 1, all the way through U at n minus 1. Okay, what is the first row? The first row, or the first block row, is of course all zeros, because in order to produce x naught there has been no action so far. And of course this x naught is equal to identity times x naught right here. No problem. What is the second block row here? This particular second block row is of course b times u0 plus everything else has not acted at all. Not yet. What is the third? X at 2. This is a to the 2. Let's go to the third. What is the third? This will be a b, and everything else is 0. Okay. What is the last one? The last one is going to be a to the n minus 1 b, a to the n minus 2 b, all the way through b. Okay. So this particular matrix is very tall. This is almost squarish, but not necessarily so. This will depend upon the various sizes of these matrices, various dimensions. Let's say U is of Rn size, okay, and X is Rn. So this is not necessarily going to be, well, you know the size. Substitute this back into the cost function. What do we get? What's the cost function here? Sorry, my bad. That was this, which is actually written in full glory on the right hand side, this object. What did we do? We eliminated the explicit dependence of the right hand of the cost function on the space variables and recast everything in terms of the action variables. What are the action variables? The action variables are these u0 through un. Okay, I've written here n minus 1. My bad. This should have been un. I have kept an n here, sum from 0 through n, therefore n over there. No problem. Is everybody with me so far? I should write here for each k. Yeah. Okay. So substitute this back here. What do we get? If I put this, if I label this as x bar, okay, let me label this, and in fact there is a, if I also keep un also at the very end, then I have to supplement here a row like that, a block matrix full of zeros. Let me label this particular object as u bar. So what do we have? We have here, this is x bar, which is this long vector of x0, x1, all the way through xn. This is equal to some matrix. Let me call this a times x0, script a times x0. This I will label as script a. Okay. Plus this I will label as rab, and I will put this as rnab for reasons I'm not going to explain. rnab here, and then u bar. That's it. Please remember that this matrix here, rnab, is fixed. This matrix here, script a, is also fixed. Yeah, and x bar now is affinely related to the vector of these inputs, which are the actions, which are is actually u bar. Yeah. So substituting back, what do we have? We had this particular cost function was x bar inert product. I believe that I have written this up somewhere here. Equivalently written as, oh, I'm so sorry. I have written here a bar and then b bar. Okay, my bad. I should relabel these. Excuse me. Extremely sorry for this mess. This is not script a. This is actually a bar, and I have labeled this as b bar later on. So this now here is going to be b bar. This is going to be plus, and this is going to be a bar. Okay, so x bar is now a bar times x0 plus B bar times U bar. Okay, and the bars are simply denoting the concatenation of several vectors. Okay, at, at let's say specific instance of let's say K. So equivalently written as this minimization problem. What is this? Well, now this is absolutely easy. It is easy because this minimization is over U bar, and all I need to do is, oh, oops, this is not X bar, this is X0. Okay, so minimize over U bar given of okay, minimization of what? Minimization of this particular cost function, which is a quadratic mapping of X bar and U bar. And how are X bar and U bar related? They are related in this particular affine way. So all I need to do is to substitute this X bar relationship in there. Yeah, and I'm going to get this is equal to minimize over U bar. This is A bar times X0 plus B bar times U bar, Q bar. Yeah, and multiplying A bar times X0 plus B bar times U bar plus U bar R bar U bar R bar. So Q bar is that particular block diagonal matrix Q all the way through Q, zeros elsewhere, and R bar is this R block diagonal matrix with all other entries being equal to 0. Subject to now there is no need to keep this. Yeah, of course there is the need to keep that. Subject to A bar times X0 plus B bar times U bar belongs to this set X, and U bar belongs to this set U bar, X bar. What is X bar? That would be a very nice question. X bar is the concatenation of all the x's, and the Cartesian product of all the x's. This is going to be n-fold, n plus 1 fold, because time goes from 0 through n. Okay, and then U bar is equal to the admissible action set, Cartesian product with itself, and this is again n plus 1 fold. So the optimal control problem here, this object at the top of OCP, optimal control problem, has now been translated into an optimization problem, which is this. Optimization problem in which variables? U0, U bar. That's it. You can feed this into a solver, and this is, as you can see, this is an optimization problem of the quadratic type, because Q bar is positive semi-definite. R bar is by assumption positive. R bar is positive definite. This is positive semi-definite. So this optimization problem is convex quadratic with certain constraints that are either ellipsoidal / affine, linear. Bona fide quadratic program. No problem. All right. Any questions so far? That's how you would solve in real life. You would solve an optimization-based problem. Okay. This OCP is transformed into an optimization problem. Now you can let your MATLAB routines do this particular, solve this for you, and out comes a sequence of optimal actions. What do you do with those actions? Well, what do you do with those actions? Interesting. So as I was mentioning, this is a quadratic problem. What do you do with those actions? And in fact, I have just explained what needs to be done. Eliminate X bar, and you get what you had to do, okay, etc. What do you do after that? Once you have solved the problem, as I was mentioning, there's the time axis, and from this point onwards until stage n, That's the length of the horizon. After solving the problem via some optimization solver, you are going to get a sequence of, let's say, U0 optimal, U1 optimal, all the way through UN optimal, UNO. Okay, there's a sequence of optimal actions. Okay, this depends on the space variable at time 0, x bar, x0. What do you do then? You act right here, send in the action u opt 0. Okay, then what? Of course, then the model really enters the fray. The moment u0 opt becomes available, the model says, okay, what is x opt at 1 going to be? This is going to be 0 plus b times u opt at 0. Okay, then we are here at let's say k equal to 0, here k equal to 0, and here k equal to 1. I should label this act with u naught of 0. So here there was x at 0. Here I have now x opt at 1. Repeat the same process. Plan ahead for n steps. This now here is n. So this instant was actually n. Here this is n plus 1. All right. Repeat the same process as before. Meaning, with this as your new initial condition, we will solve the same problem as above, as this problem. The optimal control problem, OCP. Solve it. What do you get? A sequence of optimal actions. Those actions will now be, I'm going to label them in green. I don't know, u naught at 1, u naught at, let's say, okay, 2, and all the way to u naught at n plus 1. Yeah, act here. Act with u naught at 1. Repeat the same process. Time t. From here all the way through n plus 2. This is this is actually 2, k equal to 2, k equal to 1, this is k equal to 0, etc. So the planning horizon, which is shaded in this bright reddish thing, that horizon remains fixed. It slides to the right, okay, at each k. Slides to the right by 1 at each k. Simply plan ahead and then act myopically. Planning ahead is for n steps. That's not myopic. The action is myopic because it enables you to sort of rectify immediately if you have done something wrong. Similarly, as in the case of driving, if you veered too close on the left or on the right of your lane, well, just simply rectify, and this needs to be done really myopically. The planning is okay to have a longer plan, but the actions need to be short. Okay. All right, I'm running out of time. So here, linear models. I think I'm done with the linear models. Is there any question? Let's see. Is there any question? Represent cost function. Okay, cost functions. All right. Okay. So cost functions, absolutely nothing sacrosanct about having quadratic costs. It's just for convenience. There is not really no other reason. And not just that, there are plenty of examples with various kinds of costs, even sine okay, cost functions that are not always of the same sign. That's it's going to be fine as well. Nonlinear models. I don't have much time left, so I will mumble a little bit about nonlinear models. So far, we have looked at linear models. What did we do with linear models? We recast an OCP into an optimization problem. That particular optimization problem was of a nice nature. It was a QP. Okay, and therefore it can be solved reasonably well online for medium scale problems, and sometimes also for high dimensional problems. Nonlinear models is an entirely new ball game. All right, nonlinear models would be represented like this. That's the nonlinear model. That's the nonlinear. It's this iteration. This F is your nonlinear system, which is it's evolving on the basis of its own and on the basis of the action variables that you introduce into the system. The cost function is this. I'm simply representing the objective by this letter C. It could be anything, that's your call. And certain restrictions on the trajectories. You should think of these restrictions as some kind of tubes, okay? Some kind of tubes. Let's say that this is the k-axis, okay? Time axis, and that's the space axis. In terms of a cartoon, this will look something like, okay, plum, etc. Maybe this and that and so on. So at a really discrete instance of time, let's say k equal to 0, this is k equal to 1, this is k equal to 2, k equal to 3, etc., etc. Okay, and that's your restriction. X will be restricted from here to there at 0, from here to there at 1, from here to there at okay, and so on. Same thing with you. So these are in effect certain kinds of tubes in space. Okay. Now these tubes could very well be fixed, and really by that I mean this is the time axis, and if let's say this is x moment. Excuse me. Yeah. X, and it could very well look something like that. Okay, and well, that's that. Okay, certain constraints on X and U. Now here's the problem. The problem now translates into minimization of. Is there a question?
What is the LTV model? That's the question.
LTV model is the linear time varying model. Linear time varying model will be something, well, its extension is really, okay, here I have an extra slide. LTV model would be LTV model, linear time varying model. Linear time varying. So far we were looking at x at k is equal to a times x at k plus 1. Sorry, my bad. X at k plus 1 is equal to a times x at k plus b times u of k, etc. A and b were fixed. In the case of the linear varying model, we will have a as a function of time as well. So this is xk plus 1 is equal to k, xk plus b of k times u of k. Okay, it is assumed that this AK sequence and the BK sequence, meaning A sub K as a sequence, K 0 all the way through N, and when not just that, everything is actually known. B of K is equal to 0, 1, 2, etc. These are known. Now, if these matrices are known to you, sometimes these could be repeating with respect to time, and so on. If these are known to you, then you can simply substitute as in the previous problem. This object is now going to be, okay, slightly different, but not very much. This object is going to be also slightly different, but not very much. Of what kind? Let me quickly scroll backwards. Let's see, where was I here? Yeah. So here this will be A. Well, it's no longer going to be A. This is going to be A of 1 and A of 2, so on. So this is going to be LTV case. I should probably write this here. This is going to be, okay, X at K is going to be what? A at time K minus 1 multiplying A at time K minus 2 all the way through A at time 0, X0 plus. These matrices, the order of multiplication needs to be checked, so please be a little bit careful as you do these things. Now, these block rows will of course change into something that you can readily identify with now. Well, yeah, those will come here, and the algebra will become extremely messy, but there's no leap of faith. Are you with me? Is this okay?
Yes, sir.
All right. Okay, where was I? I was in the nonlinear model. Okay. Right. And what was I explaining here? Right. So that's the optimal control problem. Equality constrained optimization problem is a natural outcome once you try to eliminate these variables. Okay. Now, elimination of these variables, as we did in the linear case, is not going to be that easy. And the resulting optimization problem, the job is to translate into an optimization problem. That's the job of optimization-based methods. However, we end up with a non-convex problem most of the times in the case of nonlinear models F. Okay, optimization problem, usually this is a non-convex, and that's not very good. So the assumptions are, okay, C is non-negative, sufficiently regular. F is our nonlinear model. It's also sufficiently regular, and then X and U are sufficiently nice. If they are not nice, then all the heavy duty lifting is going to be handed over to the optimization solver, which is not a very good idea. Well, anyway, I have probably written here, yeah, this problem isn't necessarily convex. Still, in principle, it is tractable because there are finitely many variables, only finitely many variables. Equality constraints will appear here, and inequality constraints will appear here and there. That's how this is going to really show up eventually. Solving in real time is an issue because the problems will no longer be really convex, so you have to rely on heavy-duty solvers. The major lifting is going to be done by that particular nonlinear solver, okay, nonlinear and non-convex solver. That's yeah, if you are fine with that, great. If not, then we have to do more work. All right. Nonlinear models, the algorithm is exactly the same as in the linear case, and I have already explained that. Okay, nonlinear models. I will just mumble a few things about the fact that there is an intrinsic feedback involved here. Why? Why? Because in the optimization-based method, please remember that there was a minimization of a cost function, okay? Minimization of some cost function, xk and uk, 0 through n and subject to certain restrictions. X at k plus 1 is a, let's say, f of x of k and u of k. And let's say that xk, uk restricted to lie in some sets, x Cartesian, let's say u, okay? Here, x0 enters very naturally. This is a given data. Once this is actually given, the optimization solver solves for a sequence of control actions, u opt 0, u opt of 1, etc., all the way through u opt of n. Now, every one of these is indeed a mapping of x, map of x at 0. Specifically, u naught at 0 is a map of x of 0. And that's feedback. That's feedback right there. This object is also a map of x0, which is also a feedback, but then it's feedback from the past. It's not feedback from right now. It's not feedback from x of 1. It's feedback from one step behind. Okay? So there is a natural introduction of feedback, and the actual thing is that you end up with a finite dimensional optimization problem. If it can be solved well in real time, great. If not, more work has to be done. Negative features. Optimal
Ashish,
control
this is
is...
a question.
Yes, please.
When will you go for a nonlinear model, as there is feedback linearization in a control system? I don't know if I got the question correctly.
Yeah. So I've just looked at it. The question is about feedback linearization. See, if you have looked at feedback linearization, you would know that it is not applicable to all nonlinear systems. It's not. It is actually applicable to a very restrictive class, number one. And number two, feedback linearization, everybody seems to think that, yeah, feedback linearization will solve all the problems. Absolutely false. Absolutely false. Because at the end of the day, you have a linear representation of a nonlinear model. Then you have to deal with the restrictions. How do you incorporate those restrictions, which will be nonlinearly transformed into something that is probably no longer really convex, most likely going to be very bad. Okay, I would strongly recommend that you try going, try looking into feedback linearization and try doing what is being done here. It's not easy. Not easy. Okay. Any other question? Okay, not yet. All right. So then maybe I will be given 1 more minute in order to conclude. Is that all right?
Yeah, please go ahead.
Okay. Okay, so the negative points of this approach is the resulting optimization problem has to be solved online, which naturally asks for a lot in terms of the resources. You have to be resourceful, because online solving a non-convex optimization problem of moderate size is a non-trivial task. Okay, so these have to be done online. Numerical tractability is an issue because convexity is most of the times absent in nonlinear models. And then there is this particular issue of whether this mechanism leads to explosion and slash or non-regulatory behavior and so on. Now, this is an issue that can be addressed, easily addressed. I actually wanted to do this. I also wrote down the slides, but I have no time as usual. I've planned for a lot. But yeah, if anyone would like to approach me separately offline, I will be happy to give you the references. And in any case, the references are here. That's the conclusion. And I would just like to say that this is an extremely useful method. And here are a few references, okay, pointers to the literature. That's all, and many thanks for listening to me. That's all.
Thanks, Debashish.
My pleasure. I will unshare screen now.
Yeah. So the question is, are you okay providing the PDF of the notes that you have written?
Oh, sure,
to the
sure. By all
audience?
means, yes.
Okay.
Sure,
And
certainly.
yeah, and this is to the audience. The video is going to be available anyway. Professor Debashish will provide us the PDF slides.
Yeah.
Yeah.
In point of fact, I will send them out to the organizers right now, and we can go ahead from there. Sure.
Yes. And any questions? Is your email on the PDF? In case they have questions, can they email you?
My website is, of course, on the front page.
Okay.
So from that website, one can get the mail address. Yeah, sure.
Right. So you can, and it's okay if they contact you offline.
Absolutely fine. Please go ahead. No
All right.
problem.
So with that, are there any questions? We can take one question. We have the next speaker ready to go already.
Okay.
All right. Looks like
All
no
right.
questions. So thanks, Debashish. Bye.
Have a great time.
Thank you.
Yeah.
Bye.
Thanks a
Everyone.
lot.
Bye-bye.
Bye. Bye.
My pleasure.
Professor Shimpi, hi. Yeah, hi. Hello. Okay, so give me a minute. Okay, I think we have Professor Sarkar with us.
Hi.
Hi. So I guess he's the next lecturer, and so do you want to continue, or Professor Shimpi just called me a few minutes back? I guess.
Yeah. No, I'll stop it. I'll stop it because this was just to join, Okay.
So Professor Sarkar is a professor here at IIT Kharagpur in the Chemical Engineering Department, and he is, like other lecturers, also an expert in multidisciplinary optimization, and he has kindly agreed for 2 lectures. We are very thankful to him for this. So Professor Sarkar, whenever you are ready, you can start.
Okay. Thank you. So, good evening to all of you.